we have discussed about the structural isomerism of alkenes. Now in this lecture we will move on to the geometrical isomerism of alkenes. So let's start. Geometrical isomerism. Okay. So, geometrical isomerism is a type of stereoisomerism. What are stereoisomers? The stereoisomers are the isomers which differ in the arrangement of substituents in space. Okay. So, the stereoisomers differ in the arrangement of substituents in space. So, let us say if we take one double bond, okay. So, there can be two arrangements possible. If we say that there are two groups attached to each carbon, X and Y. So, the groups can be attached like this. The groups can be attached like this also. So, this is A, this is B. So, in A, the similar groups lie in the similar side of the double bond. So, this configuration is called cis. And in this one, the same groups lie in the opposite sides of the double bond. This configuration is called trans. Okay. So, what is cis? Cis is when two identical atoms or groups lie on the same side of the double bond. So, when two identical atoms or groups lie on the same side of the double bond, then it is called cis. And what is trans? So, when two identical atoms or groups lie on the opposite sides of the double bond. So, when two groups lie in the opposite side of the double bond, then they are called trans. So, these are cis and trans. Now, if there was single bond, okay. So, if there was single bond, then it could rotate freely. So, the arrangement of the groups, suppose first of all it was like this. So, the arrangement in the next step can change to this, okay. But this is not possible in case of double bond. We had seen Newman projections and different conformations in case of alkane, because rotation was possible around the single bond, but for double bond the rotation is restricted. So, we will not be able to see these type of conformations in case of alkanes. Now cis and trans, although they are more commonly used, but cis trans nomenclature is applicable if both carbons in a double bond are containing same groups. Okay. So, let us say in both these carbons the groups are X and Y. So, here we can use the cis trans form, but if there is a carbon like this, so one has A and B, another has P and Q. So, the 4 groups are different. In this case, we cannot use cis trans configuration. Okay. Now, cis trans configuration can also be used in such cases. Suppose one substituent is common in both the atoms. So, with respect to Y, if we see Y is common in both of these atoms and they are in the opposite side. So, we can call it trans. In this case, it is possible because at least one substituent should be common in both atoms for saying the cis trans configuration. Okay. So, for cis trans, at least one substituent should be common in both carbon atoms. But if all 4 groups are different, okay, if all 4 groups are different, then we cannot use cis trans. In this case, we use EZ configuration. Okay. These are taken from the abbreviation of 2 German words. E is called Entgegen, which means opposite, and Z or Z is called zusammen, which means together. Now, if all 4 groups are different, then how will we say opposite or together? That is by the means of priorities. So, for EZ, we have to assign priorities to the substituents. Okay. We have to assign priorities. So, for assigning priorities, we will follow this rule, CIP rule or Kahn-Ingold-Prelog. This is the rule, CIP rule or Kahn-Ingold-Prelog. So, CIP rule states that atoms having higher atomic number will have higher priority. Okay. So, atoms having higher atomic number will have higher priority. By this, H will always have lowest priority. So, carbon will have higher priority than hydrogen. Nitrogen will have higher priority than carbon. Oxygen will have higher priority than nitrogen. Then the halogens. Halogens will have higher priority than oxygen. Okay, it follows kind of this order. So, the second rule of the CIP rule is that, for example, when we are assigning the priorities, one carbon is bonded to two carbons again. Okay. So, this will be tie. So, when there is a tie, we move to the next atom. Okay. How this works? Let's say this is a double bond and we have one ethyl group here and one methyl group here. Okay. So, among these two groups, which will be priority 1 and which will be priority 2. So, this carbon is bonded to both carbon atoms here. Now, if we are talking about this, for example, so this bond is with hydrogen and this bond is with carbon. So, carbon has a higher atomic number. So, carbon will naturally have a higher priority than hydrogen. So, we can assign this group as 1, this group as 2. But for this case, both the bonds are with carbon. So, there is a tie. So, we will move on to the next atom, that is, we will see what this carbon is bonded to. So, this carbon is bonded to 2 hydrogens and 1 carbon. Okay. And this carbon is bonded to 3 hydrogen. So, since this carbon is bonded to 1 carbon at least and this carbon is bonded to no carbon, there are only 3 hydrogens. So, we will give this as the priority 1 and this as priority 2. Okay. So, this is how the CIP rule works. So, let us discuss some examples. Okay. So, before examples, let us say we have 4 groups. This is 1, this is 2 for example, and in this case this is 1, this is 2. So, the first priority groups are in the same side of the double bond, same priority, same side. So, we will call this as Z or Z. That was Z means what? Z means Zusammen, that is together. Therefore, when the same priority will be in the same side, we will call this as Z. Now, say there is this carbon. So, this is 1, 2, 2, 1. So, same priority groups are in opposite sides. So, we will call this as E. E means entgegen or opposite. So, when the same priority groups will be in the opposite sides, we will call it as E. So, let us now do some examples. So, in this case, the two groups are the same. that is the groups bonded to these two carbons are the same and same groups are in the opposite side. So, in this case we will call them cis trans or EZ. Since the substituents are same, methyl hydrogen, so we will call them as cis trans and this is trans, okay, since the same groups are in the opposite sides. Now, this. So, here the groups are ethyl and hydrogen and here the groups are methyl and hydrogen. But since hydrogen is similar, although these two groups are different, but the hydrogen is similar. So, since these two hydrogens are in the same site, we will call this cis. Now, if we talk about this. So, all four groups are different. Now, we will have to assign the priorities. Let us talk about this carbon. One is chlorine and one is hydrogen. So, chlorine has a higher atomic number, so it will have first priority and hydrogen will have second priority. Now, let us talk about this carbon. So, there is ethyl and methyl. So, the methyl carbon is, both are carbons. So, we will see these next carbons again. So, the methyl carbon is bonded to 3 hydrogens and the ethyl carbon is bonded to 2 hydrogen and 1 carbon. Since carbon has a higher atomic number, so this is 1, this is 2. Now, the same priorities are in the same side. So, we will call this as Z. Okay. Now, if we consider this molecule, okay. Let us talk about this carbon. So, this carbon is bonded to 1 carbon and 1 oxygen. Since oxygen has a higher atomic number than carbon, so oxygen will have the higher priority. So, OH group will have the first priority and methyl group will have the second priority. Now, let us talk about this carbon. It is bonded in both sides with carbons. So, we will have to look into these carbons now. So, this upper carbon, it is bonded with 2 hydrogens and 1 chlorine, and this lower carbon, it is bonded to 2 hydrogens and 1 carbon. So, 2 hydrogens are common. It is bonded to 1 carbon and this is bonded to 1 chlorine. Since chlorine has a higher priority than carbon, so this will be 1, this will be 2. Now, in this case, the same priority groups are in the opposite sides. So, we will call this as E. So, we have discussed about the isomerism in alkenes. Now, in the next lecture, we will discuss about its preparation. Thank you.